Good morning. So we'll arrive at a equilibrium equation for a vehicle which has this condition. Of course, this is a very generic condition where you can incline. So you can imagine a car trying to climb an incline, and the car is also accelerating. Okay, so a car climbing an incline and it's also accelerating, and there are various forces which are coming on the car, and this car also, so also assume that you have a facility in the car where you can actually attach a trailer. There's also an hitch here. So here we'll try to see the various forces that could act on a car in this condition. Okay, now we have drawn, this is the road surface. What you have seen is the road, it is the reference, ground, and this is the road surface. This is the road surface. So I should not actually confuse you. Let me show that this is the road surface. It is the reference. It is not, it is only the horizontal reference, and this is actually an inclined road. And this road is inclined at an angle of theta. Now let us imagine what are the forces coming, and basic forces could be the weight of the vehicle. So this is the center of the gravity imagined somewhere here, and that the weight of the vehicle could act like this, which is actually W. And this weight component could be split into two components here. This is theta, of course, suppose if this is theta, this would be theta here, and the weight component W could be split into two components, W cos theta here and W sin theta. Okay, and these are the two components of the weight here. And when the car, so also said the car is accelerating. When the car is accelerating, there will be inertial forces. The inertial forces is equal to F is equal to ma, and you know that m can be written as W by G. So I have written this in this way. So these are the inertial forces. So a force required F, there's an inertial force of F is applied when you're trying to accelerate the mass of m. Now with an acceleration A, the force required is the same as the inertial force. So therefore, the force required is F is equal to ma. So m is written as W by G into Ax. As per the SAE convention, so longitudinal axis is x, and vertical axis is z, and the lateral axis is y. Okay. So I mentioned this. So we are now done with two forces here, and there's one more force. When the vehicle is going ahead at some speed, the air actually tries to push the car. So there is some pressure built up here, there is some vacuum built up at the rear. These two could be imagined as a force acting at some point. So you can't feel this force, so you can only feel this force on a car, but you can't actually see it. So we can actually calculate, or we can actually use some tools to find out where this force could be acting. Now where this imaginary center of pressure, so you can call it as a center of pressure, because air drag is basically the pressure of the air at the front and the vacuum at the rear, because there will be differential pressure. That differential pressure could be imagined to act at some point here, which you can call it as dA. dA stands for drag due to air. Okay, so it is acting at an height HA. So I forgot to say that here the center of gravity is at a height H. Okay, that there are three heights here. One is the center of gravity height from the ground, which is H. This is the height of the center of pressure of air drag, so that is HA, and also there is a hitch point here to which you can attach a trailer. This is at an height of HH, and on the trailer there could be two forces, because when you're trying to pull some trailer, you need to pull it. So this trailer would be actually producing a reactive force backwards. So we are trying to see what is happening on the car. Okay, now the car is trying to pull this, but from outside the trailer is actually trying to pull this car backwards. We want to see what is happening to the car. What the car is, so we don't want to see what the car is trying to do to the trailer. So suppose if you want to do that way, we'll feel that we are trying to pull the trailer forward. So we don't want to see that. Now what is this trailer doing? So trailer has got a mass. So suppose if this trailer has to be pushed forward, definitely the trailer will pull this backwards. Okay, that force we are writing here, that is called as the reaction due to hitch point along the x direction. Here also you see x direction, here also you see the x direction. X direction refers to longitudinal. Okay, And then there are two forces coming on the each. When you're trying to hold the trailer point, so you'll feel a weight on it. So that weight component can be called as RZ. So these are the main forces acting. Of course, you can actually count on the reactive forces acting at the wheel, but that will cancel out. So you don't have to worry. Okay, guys. Last time we actually tried to find out the equilibrium by considering about some point. So we'll try to consider about the rear wheel point like this. Okay, about the rear wheel, let us say that the car is hinged. When you know that when it is in equilibrium, the sum of the forces and the sum of the moments have to be 0. So that is the clockwise moment should be equal to anti-clockwise moments. So we'll try to see what are all the clockwise moments and what are the anti-clockwise moments now. So we'll start from the force. Okay, which was the first force we mentioned last time? Okay, in the equation. We'll go in the same order. W. Okay, W sin theta or W cos theta. Or this. Okay, it's okay. It doesn't matter. So let us go with the forces, same in here. So let us see that the car is hinged here and all these clockwise moments, the clockwise moments should be is equal to anti-clockwise moments. Or you can say that the sum of this clockwise and anti-clockwise moments should be equal to 0. So clockwise, you can consider this as positive. Anti-clockwise, you can consider this negative. And when you add these two, it should be 0. So let us actually say that way. So let us see what are the forces which are trying to make the car go clockwise. So we'll count with the first force here, WF. Now, WF is acting at a distance of some distance from the rear wheel. So we call this distance as L, which is the wheelbase of the vehicle. So please also write this. So L is the wheelbase of the vehicle. So this WF will be acting like this on a car. So imagine that this car is like a free body diagram. What is a free body diagram? Free body diagram is a diagram where you're only showing the forces on something. You're only showing the forces on something like this, and you're not showing any supports. Imagine that there is no road here. Imagine that there is no road here. There is no road. The car is actually literally flying in air with these forces. Okay, there is a force on the front wheel, there is a force on the rear wheel, which is trying to support the car. But don't imagine that there is no road. Okay, so now this free body diagram is actually where we replace all the supports with forces. There are only forces acting on the body, and thereby you can actually find out whether this is in equilibrium or not. Okay, so this is WF is acting at a distance of L about this point, which would try to rotate this clockwise. So we wrote this as WF into L. WF into L. That was plus. And then what are the other clockwise moments? So this dA. Now this dA is acting at a distance of. So there is a line of force. There is a line of force of dA. Line of force of dA. Now this line of force of dA about this point is at a distance of how much? So what is HA? So that is it plus or minus? So here you can see that it is acting like this. That will try to rotate the car like this clockwise. So then that is again plus here. So dA into HA. dA into HA. Then what about this force? This force is acting like this. Line of action is like this. So will it rotate clockwise or anti-clockwise? So that is again, it will try to rotate clockwise. So that is again plus. So W by G, that is M, into AX, acting at what distance? H distance, that is plus again. Again, we know that the weight has got two components here. So W sin theta. So that is also trying to act clockwise. Okay, that is again plus. W sin theta. Is it going out of the view? No. Okay, W sin theta into what? H. Into H. And now what about this W cos theta? It is minus. So minus. So W cos theta is only the component which is actually acting anti-clockwise. If it is acting like this, about this point it would try to rotate the car like this. So what is the distance through which it is acting? So it is not h. So it is acting like this. You now should know what is the perpendicular distance through which it is acting. Last time we wrote this as c. So we said that the center of gravity is at a distance of b from the front wheel, c from the rear wheel. Of course, we are trying to show as and when it is required, c from the rear wheel. So therefore, this W cos theta from the rear wheel point, it is acting anti-clockwise at a distance of c. Okay, so W cos theta to c. So we are done with these forces here, and of course we don't have to worry about this WR because WR is acting at 0 distance from the same point. So WR into 0, that's it, 0. And then we'll try to find out this point, and this of course hitch will be at a distance of something here. And what is this distance? Last time we mentioned. So do you remember? So we'll use the same terms. So we don't want to use any other term. So RHZ into what is the distance?
D.
Huh?
D.
DH. Okay, distance of the hitch point. Okay, so the hitch point from the rear wheel is at a distance of DH, and therefore you will see that whenever the trailer tries to apply a force on the hitch point like this, the car wants to turn clockwise. Right or wrong? If you try to push, the car will lift now like this from the front. So this, again on the right, this, okay, it is plus or minus. RHZ is plus or minus?
Plus.
That is plus. RHZ into what distance? DH. So DH. And then again this force, RHX, this is acting, now the line of force is like this. It is at a distance of how much? From this point, now from the hinge point. It is at a distance of HH. Okay, so this is plus again or minus again? This is plus again. So that is RH. So this is reaction force due to the hitch in the x direction at at a distance of HH. HH. Okay. So we are done with all the forces acting on the car now. Now for this condition, and the sum of this clockwise moments and anti-clockwise moments has to be 0. Okay, we have found out this. Now this is the equilibrium equation. This is the equilibrium equation. Now we can actually find out what is WF. If you want the weight of the front wheel for this condition, guys, here this equation is not, it is for this case. If you want for any other case, you can change it. Right now I said this car is accelerating on an incline. Since it is accelerating, the inertial force is backwards. Suppose if I said the car is decelerating on an incline, then you know that when you're decelerating, your weight will fall forwards. So that means the inertial force would have changed the direction. Now instead of this inertial force like this inertial force would have been like this. In that case, this W by G into A into H would have been minus. Okay, like this. So like this, you should be able to change the signs depending upon that. And suppose if this car was going down like this, suppose if the car was going down, then this W sin theta would have come like this. Suppose if the car is actually going like this. Suppose if the car is going down like this, and it is the center of gravity. Then what would have happened? Then there would be two components here: W cos theta like this, and W sin theta like this. And from the rear wheel, now from the rear wheel, if you are taking moments here, okay, W cos theta will be downwards, but this W sin theta, earlier it was trying to make the car squat, go back like this. Now when it is going downwards, the weight component would actually try to make this go anti-clockwise. In that case, this W sin theta sign should have been minus. Like this, we can't make equations for every case here. So I'm only showing a generic case here. Okay, you should be able to change the signs of this suitably. Okay. Okay. Now you can actually try to push all these terms, only retain WF on the left hand side to find out the weight on the front wheel. You can do that. Okay. So this case is for what? So can I say now what is it for case? Now this above equation is for what?
Accelerating on the
Car accelerating. One is car accelerating, and two climbing. It's climbing, not it is not descending, it is climbing an incline. It is climbing, and then it has got a hitch. It has got a hitch. Okay, suppose if hitch is not there, what terms will vanish? All the terms related to hitch will vanish. Suppose if this car is actually going on a flat road, not an inclined road, then what terms will vanish here? Sin theta becomes 0. Sin 0 is 0. This whole term will vanish. Okay, and this cos 0 is 1. This term will be there. Okay, like this. If it is, suppose if the car was accelerating on a flat road, suppose if I ask you to find what is the weight on the front wheel and the rear wheel when the car is trying to accelerate on a flat wheel, then these terms, this will vanish. You will see that cos theta becomes 1, because 0, flat road means theta is equal to 0. So cos 0 is 1, like that. Suppose if I say a car going at a constant velocity on a flat road, then what all terms will vanish? So flat road means this sin theta will go, this cos theta will become 1, the inertia forces will go. Suppose if there is no hitch forces also will go, and it will be like a static equilibrium problem. Okay, it will become a very simple equation. So like this, you should be able to use this equation to solve numericals. Okay, let me actually give a numerical without considering the hitch forces now. So can we solve a numerical now? Okay, please. Find the weight on the front wheel. So let me actually split this video into two.